All right, everyone, we are back and we are going to go through our lecture 10, which is all about system stability and feedback control objectives. So stability is one of the, and probably, everything's important, but stability is crucial for any control system. You need to have your system stable. You need to have the behavior controlled. We need to control, again, these dynamic systems. So we need to be able to determine, is a system stable? You've heard me hint about something about like unstable, if it's marginally stable, and we're going to figure out how do we classify that depending on the systems that we're working with. So our system stability is directly tied to the location of those poles of our transfer function. And we'll have some rules that we're going to develop to determine whether something is stable. If all of our poles lie in the open left-hand plane, LHP, we're stable. And there's some additional rules to that, but generally speaking, you're safe on the left-hand side. If you're on the imaginary axis and they are simple, basically non-repeated, then you're marginally stable. This kind of makes sense because you remember, if you're on the imaginary axis, your system is kind of like, it just looks like a sine wave, right? But if you step a little bit over to the right, you start to get that exponential increase, right? So if even one pole is in that right-hand plane, or there are repeated poles that are on the imaginary axis, so that's kind of the big distinction here. So if there's repeated poles on the imaginary axis, then we're going to be unstable. It doesn't matter how many poles you have that are stable. One pole, it's game's over, because exponential increases happen, and once you have that, it's hard to kind of take a step back. But again, this is a broad overview, and depending on the system that you're working with, we really need to kind of flesh this out a little bit more. So let's go ahead and let's start with just first order, basically system. So if I have a plant function or transfer function, that looks like this, it's first order. There's only, again, s to the 1 power. We can see if this is going to be essentially the response to the system. If my sigma is greater than 0, we're stable. If it's equal to 1, we're marginally stable, because we're just going to basically sit on that 0 point, or that 0 value on our S domain. And if it's less than 0, we're going to be unstable. So we're going to sit in that right-hand plane. So it's really, really important. We can kind of see this, and we can actually even, wonder if we have, we'll look at that a little bit later, but you can prove yourself the response of the system, and especially working with this. I quit the kernel, so it might be very sensitive right now. So let's go back. So that's essentially what we're working with. Now, let's flesh out that kind of statement we made before. So remember, if our plant function or our transfer function is stable, if and only if the p sub i's, and there could be multiple of them, from I equals 1 to, not infinite, but some number. If they're all in the left-hand plane, we are stable. So we are marginally stable if all of them are in the left-hand plane or on the imaginary axis for all I, and there's some non-repeated values. So that's really, really critical. Additionally, that's if we're marginally stable. We're unstable if and only if some of the PIs are on the right-hand plane, or we have repeated PIs on the imaginary axis. So we can look at some example systems and see if they're stable. So let's look at the first system. I wish I would have basically put something over this, but all on the left-hand plane, stable. What about this function? Pole is going to be -4, and definitely stable. What about here? Definitely stable. Why are we saying this is marginally stable? Because on the imaginary axis, we have some non-repeated poles that are located there. Marginally stable. If they're repeated, at least as far as we can see, there's no like superimposed repeated one, then we'd be unstable. Here, pole in the right-hand plane, unstable. Here, pole in the right-hand plane, stable. Additionally, if I had something like this where I had this and then another one right on top of it, it would be unstable as well. So we can basically generate a very simple or very straightforward rule for essentially those values. If I have a first order transfer function, as long as a is greater than 0, we're stable. If we are dealing with a second order transfer function, as long as a1 and a2 are greater than 0, we are going to be stable. The complication comes when we are dealing with nth order transfer functions. So anything greater than second order, we're going to have to actually develop what's called the Routh-Hurwitz stability criterion. It is a computationally somewhat intensive, or at least laborious by hand method. It's not as easy as the other ones, but again, it's very important that we're able to develop this toolkit in order to analyze the system. So we're going to develop that in the next video, and we will see you next time. Thanks. Bye.